I'm going to speak on magic squares today. So we'll take a small example before we dive into the concept. So here is an example. So Indiana Jones has found a treasure chest filled with 325 gold coins. To keep tab of his stage treasure, he has put them in 25 boxes, numbering them from 1 to 25, such that each box will contain as many coins as its number. So that means if I have box number 4, it will contain 4 gold coins. If I have box number 10, it will have 10 gold coins, and so on. Later on, he decides to distribute these boxes among 5 of his students such that each of them will get equal number of coins. So you can see that equal number of coins meaning 325 by 5, which turns out to 65. So each student should get 65 coins. So he has to distribute these boxes so that every student of his, all 5 students of his, get 65 coins each. So how will he distribute these boxes? Okay, so can someone answer this question? Try this particular problem. What can be the possible answer? Okay, so I'll tell you what the answer is. The answer is magic square of 5 by 5 order. So, okay, so I think you have seen this somewhere. So I have just changed the problem little bit, just kept the values intact. So this is in fact taken from one of the puzzles that sir has discussed when he discussed games and puzzles, something relating to cows. So farmer has some cows which he numbered them from 1 to 25 and so on and so forth, if you all recall, right? Yes, right. So that's the same problem. I have just twisted that story, and the answer that you get is the same thing. So you can either give 17, 23, 4, 10, or box number 11 to the first student, 24, 5, 6, box number 12 and 18 to the second student, and so on and so forth. Or you can go row wise. Okay, the reason this will work is because if you take every column and total up all the numbers in the grids, that will sum up to 65. Same goes for the rows as well. If you notice carefully, it has an additional property that if you look at the diagonal, okay, numbers on the diagonal, both the diagonals rather, those number also turn out to be, that sum also turns out to be 65. So this is 17, 5, 13, 21 and 9. So that also turns out to be 65. So this is a peculiar quality, it is a defining property of a magic square. Okay, so what is a magic square? It is a series of numbers which are arranged in such a way that sum of each row, each column, and both of the diagonals turned out to be the same value, and that value they people call that value as summation. Okay, so here in this particular problem, uh, every row, every column, and both the diagonals, they turn out to be, excuse me, they turn out to be the same value, and that value turns out to be 65. So 65 they call it as summation. Okay, so how did this concept of magic square come into play? So history says that this concept is not very new. In fact, it's a very old concept. So if you go back, so the first occurrence of magic square was dated to in about 650 BCE in China. Okay, so some scriptures of Chinese literature were found, and in that there was a story about an emperor called as Emperor Yu. So it's a very interesting story. So one day, what happened? This Emperor Yu was walking along the banks of a river called as the Yellow River. So when he was walking, suddenly the river started to flood all of a sudden. So he tried, so he was an emperor, so he's supposed to protect his kingdom. So he tried to avert the flood towards the sea, but somehow he was not able to do so. Uh, but what happened miraculously during that time, uh, out of the water of the Yellow River came a turtle which had some inscriptions on its shell. Okay, so these were the inscriptions on its shell, right? Using those inscriptions, he was able to avert the flood. Okay, so this is called as the low shoe uh, magic square. So the name of these inscriptions, these are called as low shoe. Low means yellow in Chinese, and shoe is scroll. So this is scrolls of the Yellow River, something like that. But now if we go on to look at it mathematically, this is nothing but a magic square, right? So what magic square is this? So this is, so you can see this is 4. So this is 4. Then I have 9, and then I have 2. Then I have 3, 5, and this is 7. And then I have 8, 1, and 6. Okay, so now you can see that this is a magic square of 3 by 3, right? Uh, if you look at the row sum, this is 4 plus 9 plus 2, so that turns out to be 15. For every row, you can check that the sum turns out to be 15. Same goes for every column, and same goes for the diagonal, right? So the Chinese believed in some concept called as yin and yang. So the even numbers, they were depicted by black dots or the yin symbols, and the odd numbers were depicted by white dots, which depicted yang symbols. So using yin and yang, some energy, he was able to avert the flood. So the Chinese believed that magic squares were in fact magical. So they had powers to avert floods. Okay, so that was way back in 650 BCE. Now, this concept was apparently known to Indians as well. Okay, so in Hindu literature, in Hindu religious practices, most often you come across something. I don't know how many of you have seen this. This is called as the Lakshmi Ganeshan. Okay, so I don't know how many of you have seen this, but in Lakshmi Ganeshan also, this is some religious tab that you get, uh, which supposed to bring wealth and good luck, right? So something called as Kuber Yantra also has this same inscriptions on it, and if you look closely, you can see a magic square occurring over here. Okay, right about here. So that square is in Hindi. You can just check out that. So this is 6816. This is 357 and 492. Okay, so again, this is a magic square of order 3 by 3. Okay, so not just in Hindu religious practices, apparently magic squares were occurring in Jain practices as well. Okay, so this is a photograph of the Parshvanath temple in Khajuraho. This was supposedly around 12th or 13th century BC, and on one of the walls, you can see this particular square occurring. This is a 4 by 4 grid of numbers which is from 1 through 16. So this grid is 4 by 4 filled with numbers from 1 through 16, and they are arranged in such a manner that the row and the column sum turns out to be the same. Okay, so this is a magic square, but now weirdly enough or oddly enough, so far in history, people were coming across magic squares of order 3 by 3. This was first time in history that people were coming across a magic square of even order, that is a 4 by 4 magic square. This was a 4 by 4 magic square. Okay, so this is also called as the Chautisyantra. The reason it is called as the Chautisyantra is because the row sum, or if you look at any of the column sum, that turns out to be 34, which is called as Chautis in Hindi or in Marathi. Okay, but here there is one peculiar aspect, that this is not quite satisfying all the properties of magic square. So if we look at the definition that we've just now described earlier, the definition says that row of the sum of each row and the sum of each column has to be the same, along with the sum of both the diagonals. So in this particular magic square, you can notice that the row sum and column sum turns out to be 34, but the same cannot be said to be true about the diagonals. Okay, so here the diagonals do not possess that property, that the diagonal sum is coming out to be 34. Uh, Now, it is said that the concept of magic square was quite known to ancient Chinese people and ancient Indians and even Arab merchants. So, via the Arab merchants, they were basically traders. So, via the Arab merchants, it is said that this particular concept of magic squares propagated to the Western countries, propagated to Europe. Okay, so you can see that by the 15th century, this concept was well deeply rooted in the mathematicians and inventors of that time. So you can see here this on the left side. Okay, this is a very famous engraving by a German Renaissance artist by the name of Albrecht Dürer. Okay, so this is entitled Melancholia 1. Okay, and this was done in 1514. Okay, so you can see this particular engraving at the top right hand corner there is a small square. So I've blown it up here. This is a zoomed in picture of this square that you can see. So you can see again a 4 by 4 square which is occurring. Okay, so this is again a magic square. If you look at the row sum, the column sum, and in fact here you, even if you look at the diagonal sum, that turns out to be equal to 34. So this is therefore called as the Dürer's magic square. Okay, and the main part of this is it has lot more properties which we'll discuss shortly. And one of the qualities of this particular engraving is, if you look at the bottommost row, so you can see the year in which this particular engraving was made, which was 1514. Right, so that was really smart of Dürer to incorporate all of these, all the properties of magic square along with some additional properties and the year of his engraving in the bottommost row. Okay, yeah. Now we come across a square which is not quite a magic square that somebody comprehends. Okay, so far in history we have seen squares which were mostly containing numbers like this. So numbers from 1 to 16 for a 4 by 4 square, numbers from 1 to 9 for a 3 by 3 square, or some other random numbers which are occurring in a 3 by 3 grid or a 4 by 4 grid. But now there was an occurrence of a lettered magic square. Okay, now how do we even define a lettered magic square? Lettered magic square is, for example, this is a very famous square which is called as the sator, or sometimes it is also called as rotus square. So what happens is, if you look at the first row, so how is it considered to be a magic square? So you look at the first row, it is SATOR. Now you look at the first column, this is also SATOR, so that is sator, and this is also sator. Now you go ahead for the second row and the second column. Okay, so second row and second column is AREPO, AREPO. So AREPO. So in the second row as well as the second column. The third row is TENET, and again here it is TENET. In the fourth you have OPERA, opera. In the fourth row also you have opera. In the fifth column you have ROTAS, rotus. In the last fifth row also you have rotus. Now it may seem to be quite meaningless. This was found in the first century AD in the ruins of Pompeii. It seemed quite meaningless earlier, because you are just taking some 3 words and you are just writing it so that you get the same thing over and over again. But it is a lot more than that, because these are all meaningful words. Okay, you take any 3 words and you can generate a lettered square out of it, but all of these are meaningful words. Okay, so I have written down the meanings of all of them. I think it is Latin. Sator stands for cedar. Okay, so something who is implanting some ideas in the human mind. Okay, and then you have Arepo. Arepo is apparently name of code name of some Egyptian god. Tenet, this tenet. Tenet means somebody who preserves, somebody who masters, or somebody who holds. Okay, and this opera means somebody who works, somebody who cares. And rotus means somebody who causes to rotate, okay, so causes to turn. Okay, so all of these are meaningful words in Latin, and specifically this middle word, T-E-N-E-T, tenet, those are said to form the arms of the Holy Cross. Okay, because this word means apparently to hold or to preserve, somebody who preserves us, something like that. Now, this was first found in Pompeii, the ruins of Pompeii, but if you, this had a very big impact in Western Europe, specifically during the rise of Christianity. So what happened was this particular square, magic square, lettered magic square, was used for protection against fire, sickness, disaster, and so on, right up till 19th century. So you can imagine the impact of this particular, that this particular square had back then on the people, right? It is so in fact in many churches in France and Italy specifically, you will find this particular satyr, or sometimes it is called as the Rotus square, is engraved on churches. Okay, so this is one particular peculiarity where we have an occurrence of a lettered magic square. I've been told by one of my friends that if, when we were little, they used to play around with Marathi words or Hindi words. For example, Guruji, or what is that? Guruji, Jilebi, and Rumala. So you can write these three words so that you can form a lettered magic square like this. So I don't know how many of you have tried that, but you can try it just for fun to prepare, make a lettered magic square using some words. Okay, now comes so up till now, till this part, right till the 19th century, the magic square was looked upon as something to do with religion, something as a, you know, protective charm or tool of a tool of divination. But after 19th century, uh, it was looked upon more in terms of mathematical interest. So the, you can see most of this particular mathematician's work was on magic square. Many, I mean to say that he worked on magic squares a lot, in fact. And you can see this particular photograph is taken from the Ramanujan Museum in Chennai, which is located in Chennai, and beneath his photo is his famous magic square. Okay, so this is a magic square that he has created, and the peculiar quality is so far the squares that we have seen contained numbers from 1 to n square. So 3 by 3 squared magic square contained numbers from 1 to 9, which were arranged. Similarly, 4 by 4 magic square contained numbers from 1 through 16. So this is a peculiar magic square because it contained any random numbers, and in fact the first row of it contained Ramanujan's birth date, which is 22/12/1887. Okay, so a lot of his work was based on magic squares, and in fact you can see in one of his notebooks he has given detailed methods in order to create such random magic squares. Okay, numbers, so which contained numbers which were other than 1 through n square. Okay, so this is one excerpt which explained techniques for creating a magic square of odd order. Similarly, he has given techniques for creating magic squares of even order and so on. Okay, so now that we know that after the 19th century, magic squares were considered as tools of mathematical interest, people start to look at mathematical properties of these magic squares. So once they started looking at mathematical properties, they started to play around with it, and they classified these magic squares into different kinds. Okay, so what different kinds? So I have given only a few kinds of magic squares over here. The first is associated or regular magic square. Then you have Latin or diagonal Latin squares. Then you have Franklin's magic square and Nomon magic squares. Okay, so let me take you through all of these squares one by one. There are not many more, but I will show you what are these four in particular. So basically, these are magic squares. That means the three properties of row sum, column sum, and diagonal sum to be equal. Along with these three, it has some additional properties. Okay, so for example, if you look at the regular magic square or associated magic square, you have a magic square, but it has an added property that you look at any two diametrically equidistant cells, their sum turns out to be the sum of the first and the last term of the series. Okay, so a very good example of that is the Durer's magic square that we had seen. Okay, so what do you mean by this? So you look at two quantities which are diametrically equidistant. So 16, so I have 16 over here and I have 1 over here. So 16 plus 1, they are diametrically equidistant. So that sum turns out to be 17. Then I have 10 and 7. They are also diametrically equidistant from each other. 10 and 7 is again 17. Okay. Then you look at this diagonal also. So you look at 4 and 13. That sum is also 17. And along with that, you look at 6 and 11. That sum is also 17. Okay. And what is the sum? So this grid is containing the numbers from 1 to 16. So the sum of these diametrically equidistant cells turns out to be 16 plus 1. So that is nothing but n squared plus 1. So the sum in fact turns out to be n squared plus 1. So this is 16 plus 1, which is 17. First and the last term of the series. Okay. The next kind of magic square, so this is a different kind of magic squares. These are called as Latin squares. Okay, so what is the meaning of Latin squares? So far in these examples, for example, if you have a 4 by 4 magic squares, then this was containing numbers from 1 right up till n squared. Okay, so 1, 2, 3, 4 till 4 square, which was 16. But now Latin squares are those magic squares which contained only symbols from 1 to 4, and they are so filled that each row and each column, they contained the numbers from 1 to 4 exactly once. Okay, so for example, if you look at this Latin square of numbers, so in the first row I have 1, 2, 3, 4 written exactly once. Similarly, in the column 1, 2, 3, this column also 1, 2, 3, 4 appears exactly once. Same goes for the second row, second column, that also appears exactly once, and so on. But if you notice the diagonal here, the diagonal is containing 1, 1, 1, 1, and here also the other diagonal also contains 4, 4, 4, 4. So they are having repeated numbers here. So for that, there is also something called as a diagonal Latin square. In diagonal Latin square, even the diagonals have the numbers from 1 through 4 exactly once. Okay, so for example, if you look at this Latin square of suits, for example, so each of them, instead of the numbers 1, 2, 3, 4, they have 4 suits. So that is spade, heart, diamond, and club. So in each row and each column, you have spade, heart, diamond, and club occurring exactly once. But here, if you look at the diagonal, okay, so in the diagonal also, spade, heart, uh, diamond, and club, they are occurring exactly once. Same goes for this diagonal also. So this is a diagonal Latin square. Okay, so even this Latin square of denominations meanings, this is ace, king, queen, jack. So you have in the first row ace, king, queen, jack. In the first column also ace, king, king, queen, jack is occurring exactly once. Same goes for the diagonals also here. Okay, which is not like this case. Okay, so ace, queen, jack, and king is occurring exactly once along this diagonal as well as along this particular diagonal. So this is called as a Latin square. Okay. Uh, Yes. Now this kind of square is peculiarly very interesting. This is called as the Franklin's magic squares. Uh, I think many of you have heard of the US president Benjamin Franklin. So he was a very big man. he was a scientist, he was an inventor and mathematician at heart, uh, and of course a great politician. So it is said that he invented magic squares which had lot many interesting properties along with the standard properties of magic square. Okay, so what happened was, it's said that it's not very clear when exactly he found this concept of Franklin's magic square, but it is said that in around 1736-37 he was working as a clerk in the Pennsylvania Colonial Assembly. So there he used to get bored because people used to, quarrel about some bills which were to be passed and so on. So to pass his time, he started working with magic squares, and he was so impressed by the properties that these magic squares can produce, that he used to call them as magically magic squares. Okay, one magically magic square. So what he did was, he was very much impressed. He did lot of work on magic squares, and in around I think 1752, so almost you can see 20 years had passed when he was working on magic squares. He wrote a letter to his one of his friends, and his friend was so impressed by his work on magic square that he published Benjamin Franklin's work in a magazine called as Gentleman's Magazine back then. And so you can see the date over here. It is, I don't know whether it's not visible properly, but it is 1965. This particular article was published, and it was entitled Memoirs of Benjamin Franklin. And I will show you. So this is a 16 by 16 magic square. So far we have seen 4 by 4, 3 by 3, which contain numbers from 1 to 9 or 1 to 16. So this is a 16 by 16 magic square. That means it had numbers from 1 to 16 square. Okay, so what all properties? So this is a very difficult magic square. So let us see what all additional properties Franklin saw in these particular squares. So the same magic square, now this is in a pretty visible format that I have put up here. So you can see these colored squares. Okay, so these white colored squares that you can see here. So 64, 223, 30, 253, like that. It goes on half a diagonal up, and it is coming back half a diagonal. Okay, so if you look at all such half diagonals going up and coming down, going up and coming down, that sum is same as sum of each row, each column, and every diagonal. So this is a very interesting property. Similarly, if you look at half a column, or even if you look at half a row, that sum turns out to be half the total sum of every row or every column. So this was also again, so along with these two properties, there were many other interesting properties that Benjamin Franklin did. So this was a 16 by 16 square. This was the biggest magic square that he had done during that time. And he was so much interested in magic squares that he extended this concept beyond magic squares. So he made magic circles also. So if you are interested, you can Google it, of course. So Franklin's magic circles. So you have circle and you draw some diagonals and try to create something similar to magic square. So this was Franklin's magic square. Now these are known magic squares. And what is the meaning of known magic squares? They are normal magic squares, but along with their usual property of each row and row sum, column sum, and diagonal sum equal, you look at the corner grids. Okay, so these four grids. Okay, so I think we have looked at this. This was the Chautisyantra, similar to the Chautisyantras. In fact, if you notice carefully, this is in fact the Durer's magic square, right? So this has the peculiar property that what was the total? Each row is 16 plus 3 plus 2 plus 13. So here each row, each column sum was 34. Each row, each column sum was 34. But now if you look at this corner square, 16 plus 3 plus 5 plus 10, that is also 34. If you look at this corner, that sum also turns out to be 34. This corner sum is also 34, and this corner sum is also 34. Okay. Along with that, if you look at the middle square, 10, 6, 11, and 7, that sum is also coming out to be 34. So this is called as the gnomon. This is a property for a gnomon magic squares. Okay. Okay, so now we have seen enough of history about magic squares, how they are classified. Now we'll actually look at whether we can create some magic squares of our own. Okay, so I will discuss two methods for magic squares of odd order. Odd order matlab we are discussing squares of order 3 by 3, 5 by 5, 7 by 7 and so on. Okay, the first method that I want to discuss is called as the De la Louvière method or the Siamese method. Okay, there is a very interesting story to this. You might be wondering why this new big name De la Louvière or Siamese method. So there is an interesting method. De la Louvière was a French diplomat, and he was visiting the kingdom of Siam in about 19 in about 1693. So while returning back from Siam, uh, he had learned the concept of magic squares. There was a Siamese method for creating magic square of odd order, but he was not able to quite get the hang of that particular magic square. So along with his envoy, he had a fellow Frenchman, fellow traveler. He was a doctor, I think. I'm not sure what was his name and something. But this doctor, he said, I know you're trying to find a method for, or you have some method for making a magic square of odd order, but I have learned one method from India and that worked very well for me. I can show you that method. So he showed him the Indian method for making a magic square of odd order, which he had learned apparently from the city of Surat or something. So when he came back, he was so impressed that he published a book, some new relations with the Siamese kingdom, something like that, a book of by that name. And in that he published these methods, the Siam method as well as this method, which he also called as the Siamese method. Okay, because he brought back this particular method while he was returning from Siam. This method is also called as the Siamese method. Okay, and because he is the one who published it, it is known by his name, which is De la Louvière. Okay, so what I'll do is maybe I will stop sharing my screen for 1 minute so you can see how we go about doing this. Okay, so can all of you see this? This is visible. So you can see there is a 3 by 3 grid that I'm holding. Is this visible to all of you?
Yes, yes,
Yeah,
we can
yeah.
see. Yes, yes,
Okay,
visible.
okay. So I'll tell you exactly how to do this, how to make a magic square out of this 3 by 3 grid using the De la Louvière method. Okay, so what you do, the first thing that you do is you look at the topmost row and the middle entry over there. So you put the first entry, which is number 1. Okay, so I write 1 here. Okay, the next thing that you go on doing is you start writing the numbers 2, 3, 4, 5, 6 and so on to the cells which lie to the northwest of that particular cell. So for example, I have number 1 here. Whichever cell is to the northwest of 1, I write the number 2. But you will tell me here there is no grid which is lying to the northwest of the number 1. So what do I do? There is a simple trick. So I fold it this way. Can you see this? I fold it this way so that the two sides are joining. Okay, so now if I look at this one is here, and to the northwest there is a cell here. If I hold on to that cell and let us see what that cell is. So that cell is this cell. Okay, so I write 2 over here. So I write 2 here. Is this okay? Now once again I look at the cell which is lying to the northwest of 2. So once again you will tell me, okay, there is no cell to the northwest of 2. So what is the trick now? Now what will I do? I will fold it this way. I will fold it this way. So now 2 is here, 2 is here, and to the northwest of this, that means it is this cell, this cell. Can you see this? This is 2 here, and to the northwest is this. So I hold on to it, that is this particular cell. So I write 3. So I'm writing 3 now. Okay. Now once again I look at the northwest cell. So northwest cell is this. Northwest of 3 is this 1. But now this cell is already filled. Sorry, northeast. Northeast, northeast. Sorry, sorry. I'm saying northwest. I'm sorry. It should be northeast, northeast, northeast of that. So northeast of that is one. So one is already there. So that is already filled. So what I do is, since it is already filled, I will look at the cell which lies immediately below this number. So I will write 4 here, 4 here, 4. Okay. And now after 4, the cell which lies immediately to the northeast is 5. This is empty, so I can write 5 here. Cell which lies immediately northeast to 5, 6, so I can write 6 here. Okay. So now there is once again no cell to the northeast of 6. So what I do again, go by my method, my trick. So now this is 6 here. This is 6 here. Again, I cannot find any cell to the northeast. Again, if I go this way also, I cannot find any cell to the northeast. So now I am stuck. So what do you think I should do? Once again, use the same technique. There are no more cells to fill to the northeast of 6. So once again, I will write 7 here, directly beneath 6. Okay. So now I have two numbers left, 8 and 9. So now what I do? Again, go by my technique. Again, I am folding it this way. So here is your number 7. Northeast of that is this. This is empty. So 8 should be here. Okay. So now there is only one cell left. So I'll write 9 over here. Okay. So this is my magic square which is complete. So if I look at the first row, this is 8 plus 1 plus 6. So this total turns out to be 15. Second row, 3 plus 5 plus 7. Total is 15. Third row, 4 plus 9 plus 2, again total is 15. You look at any column, 8 plus 3 plus 4, 15. 1 plus 5 plus 9, this is 15. 6 plus 7 plus 2, this is 15. You look at any diagonal, that sum is also 15. Can you see this? So have you understood this method? Does it look pretty easy?
Yes, yes.
Yes. Okay. So now likewise, so this was a 3 by 3 square. So likewise, you can try to make a 5 by 5. Okay. So not always you have to hold up a paper like this and go on flipping and rotating. You can quite well imagine this and try making a 5 by 5 square. Okay. So you can start with this middle square. Maybe I'll write with some other colored pen. Yeah, so you can start writing 1 to the middle of the topmost row. Okay, so you look at the northeast northeast column cell over here. So if I fold it this way, which would be the northeast column? It would be this column, right? If I fold it just like I did. Okay, so 2 will appear here. Okay, then northeast to that 3 will appear here. Okay, now there is no more column to the northeast of 3. So I fold it this way, right? And the northeast of that, this row will appear. This particular cell will appear to the northeast if I fold it this way. Okay, so 4 will come here. The northeast of that, 5 will come here. So now there is already a row which is already one there. So what I will do, I will look at the cell which is immediately beneath it, write 6 there, then 7 here, 8 here. Okay, then immediately northeast of that will come. If I will have to fold it this way, then this row will come. So 9 will be here. Okay, so what would be next? So I fold it this way, 10 would come here, right? So now that this row is already filled, that means 11 will come here, 12. So this would be 13. This is 14. This is 15. Okay, so then no more to be filled. That means 16 will come here. Okay, if I fold it, 17 would come here. That means 18 would come here because there's no more rows to be filled on top. But if I fold it this way, then this row will come. Okay, so 18 would come here. Then you have 19, 20, right? So no more rows to be filled to the northeast. So 21 would come here. 22 would go there. Then I need to fold it this way. So 23 would come here. 20, this is 23, 24 would come here, and the last one would be 25. Okay, so this is a 5 by 5 magic square which I filled using this de la Lubier method or the CME's method. Is this okay? Yes? Okay.
Very interesting, huh? Thank you.
Thank you, thank you, thank you. There is one more method which is even more interesting than this, and it is very easy in fact. So you look at this second method. This is called as the de la Hires method or the pyramid method. Okay. So what you do here is, the name is suggesting it is called as the pyramid method. So what you do is, you make every side of this square into a pyramid shape. Okay, every side of this square you turn it into a pyramid shape, meaning what? So now this is the base of the pyramid, so I have to make a brick on top of it like this to make it into a pyramid. So this looks like a pyramid. Same goes for this side. I'm making it into a pyramid. Same goes for this side, making it into a pyramid. Same goes for this side, making it into a pyramid. Okay, now you notice excuse me. Now you notice I have diagonal over here. So I get some diagonal here. So along the diagonals, I start writing numbers from 1 through 9. Okay, so this is 1, this is 2, this is 3. Now this is 4, 5, 6, and then you have 7, 8, and 9. Okay, the next thing that you do is you try to wrap up this. Okay, how do you wrap up this? So you take this one and you place it here. Take this 9 and you place it here. Okay, so maybe I'll write the square on this side. So you have this original 2, 6, this is 5, 4, and 8. Okay, and those that were outside, so this 1 is coming here, that means 1 I will get here. This 9 comes here, so 9 will go here. Okay, then this 7 will go here. 7 goes here, so I will get the 7 here, and this 3 goes here. Okay, so 3 will come here. So once again, this is a different kind of a magic square than the square that we had seen earlier. Okay, so this is, you can check again, this is 2 plus 7 plus 2 plus 6. So once again, this is total is 15. 9 plus 5 plus 1, this is 15. 4 plus 3 plus 8, this is 15. So same you can check for every column and every diagonal. Okay, so this is called as the pyramid method. You can try doing this for 5 by 5 square. Okay, so for 5 by 5 square, shall I show it to you or do you want to try? Okay, maybe I'll show it to you. This is a 5 by 5 magic square. So this is this dark black square that you can see here. That is the original square, 5 by 5, and you make it into a pyramid. So this is 3 and this is 1. So every side you are making it into a pyramid, and along the diagonal you go on writing numbers from 1 through 25. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. Okay, so now you have to wrap up this package, wrap it up like a package, and you take this one. Where will you put it? You will put it here. You take this 6, you will put it here. You take this 2 and you put it here. Okay, so this 1 went here, 2 went here, and 6 went here. Okay, same goes for this side also. This 25 would go here. Maybe I'll use a different. So 25 will go here, 20 would go here, and 24 would go here. Okay, so this is 25 is going here, 20 is going here, and 24 is going here. Okay, same for the uppers also. So you take this 5, you place it here. Take this 4, you place it here. Take this 10, you place it here. 5, 4, and 10 are placed here, and then you get a magic square. Okay, so this is the pyramid method. It is more easier to understand than the CME's method, but CME's method I find it more interesting. Okay, the next method that I want to show you is for magic squares of even order, particularly magic square of 4 by 4 order. Okay, so this is very easy, because if I look at 6 by 6 magic squares, or even higher order, even order magic square of orders more than 4, the technique becomes a little bit more difficult. So I don't want to discuss that technique, but you can of course find it. Google is always there, and I will show you some references maybe later. So now we have a 4 by 4 magic square. We want to create a 4 by 4 magic square. So how to do that? Okay, so what we do is you go on writing numbers in this grid continuously from 1 till, this is 4 by 4, so 1 through 16. Okay, so you have 1, 2, 3, 4, then you have 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. Okay, for creating a 4 by 4 magic squares, you look at these entries. Okay, so 2, 3, 8, 12, 14, 15, 5 and 9. So you write those entries as it is over here. Okay, so you get 2 here, 3 here, then you get 8 here, 12 here, 14 here as it is, 15 here as it is, 9 here as it is, 5 here as it is. Okay, so let us see what do we do of the remaining entries. So you look at the entries which are cross diagonal. Okay, so those entries which are equidistant, you flip them. Okay, so that means 16 goes here, 1 goes here. Okay, so that means 16 is here, 1 goes here. Then 13 goes here, 4 goes here. That means 4 is coming here and 13 goes there. Okay, same goes for these two also. So 16, 6 comes in place of 11, 11 goes in place of 6. So this is 11 and this is 6. And you also have to flip these two. So this is 7 and this is 10. All right. So now you check whether this is a proper magic square or not. So you look at 16 plus 2 plus 3 plus 13. So the total turns out to be equal to 34. Okay. So yeah. So you are getting 34 as each row sum, each column sum, along the diagonals and along the cross diagonals. Okay. So you are getting your correct answer. All right. So I hope this technique is clear for 4 by 4 magic square, right? Okay. Now that we have discussed some techniques for generating 3 by 3, 4 by 4, 5 by 5 magic squares, we'll look at some variants that you may have come across earlier. Okay, so do you all know what this is? Have you
Ma'am,
come
can I
across?
interrupt for 1 second, please?
Yeah, sure, sure.
Yeah. I wanted to know regarding 6 cross 6. This will not work for 6 cross 6.
This is not working for 6 by 6. 6 by 6 and 6 by 6. Then there is 10 by 10. So even squares of the order 4k plus 2, there is a different technique.
Okay.
So I'll tell you where you can find that technique. So you can probably go through that.
Yeah.
I'll tell you. Yeah, I'll tell you. Yeah, so yes, this is Sudoku. Most of you guessed it right. So Sudoku is also a magic square basically. The French people started working over magic squares. So this is a Latin square, what we had discussed earlier. So this is a 9 by 9 grid, but it does not contain numbers from 1 through 81. It contains numbers from 1 to 9 only, but they have to be so arranged that each row and each column has exactly the numbers from 1 to 9, right? So what the French people tried doing was they started formed a 9 by 9 Latin magic square, and they removed numbers in between and then asked people, okay, can you solve this now? This was developed in around I think 1979, and this became really popular in Japan, okay, in the 1980s. So it became so popular that a Japanese Japanese puzzle company, they said, okay, this belongs to us, and we are now going to call this as Sudoku. So Sudoku is a Japanese word. Okay, so after that, Sudoku became a lot more popular. Okay, there is another variant of magic square that you might have come across. It is called as Sujiko. I don't know how many of you know this. Do you know this? Sujiko. So Sujiko is you have a 3 by 3 grid, 3 by 3 magic square, but there are circles over here. Okay, so this is a magic square. That means row sum, column sum, and diagonal sum have to turn out to be same. But now, along with that, what is given is you look at these circles. That means you look at these four numbers. Their sum should add up to 70. Now, this is a filled Sujiko puzzle, obviously. In the puzzle, they remove out the numbers here, and the only thing that is given is some numbers inside the grid and this summation. That means whatever numbers you fill in these four grids, those should sum up to 17. Similarly, whatever numbers you fill up in these grids, those should sum up to 18, and so on. So this is Sujiko. This was generated by a Korean person in 2010. So this is quite recent. So magic squares, I always feel those are ancient tools which were used for religious purposes, but now they are of so much of a mathematical interest that they have applications, lot many applications in cryptography, in music, and so on and so forth. Okay, so they are a perfect example of something which originated way back like in 650 BCE, and it's still stuck on even today because it had great many applications. So with that, I end my lecture, and I hope you enjoy it. Thank you for your patience listening.
Yes, ma'am, it was really very interesting. Thank you very
Thank
much.
you so much. So these are the references. So you can see the first reference is a bit I don't know, maybe easy for some of you. So the 66 by 6, 10 by 10, those techniques are given in this. So Andrew, this is by W.S. Andrews, and the title is Magic Squares and Cubes. So this has even some concepts of Benjamin Franklin's magic squares, magic circles, and there is something also called as magic stars apparently. So you can check that out in this book just for fun. The second reference that I have given, that's a children's book. Okay, so something about some stories about Franklin are given, and not necessarily those are historically correct, but those are meant for children. And this technique, the Siamese method, is given explicitly in this particular book for creating 3 cross 3 square. And lots of material can be found on Britannica Encyclopedia on history of magic squares. So you can probably go through these. Thank you so much.